Integration application part 2. Areas and volumes. These are Calc 1 ideas. I don't want you to be rusty because they are definitely on there. Okay, first, when I say area, you need to differentiate between two types of questions. If I said one question is find the area enclosed by y equals x squared minus 4 and the y-axis, or if I said evaluate this integral, negative 2 to 2 of x squared minus 4, certainly there's a ton of overlap, but there is a difference. If the question says find the area, then it is implied your answer must be positive. It's got to be positive. Volumes are positive also. Must be positive, and so you would take steps to make sure that happens. For example, rather than straight up integrating, you would probably say, well, shoot, those y's are negative. I need to take steps to make them positive, and so you'd do some kind of negating it or switching the signs of the integrand. I'm not a big fan of switching these limits. That to me is weird and artificial, but you would take some steps to make it positive. And when I say make it positive, I don't mean take your eraser and change your answer to positive. I mean make your work come out to be positive. Is that understood? Yes. Okay. Rectangles or y-slices, again, when you, if you were to look at area under a curve here and use rectangles, and the rectangles are oriented this way and super thin that way, is that a delta x or a delta y? That's a delta x, and so if your rectangles run that way, or your slices, I don't even draw rectangles, I just draw stripes, then you're talking dx. If your region, whatever it might be, runs, you decide to run this way for a reason we'll talk about, well then the height is the differential, and so the height is delta y, and you would use dy, and y is the limits of integral, right? What goes in your mind when you choose x or y? Sometimes you can use both, and it's not the same, but what might swing it one way or the other? Okay, one is the nature of the function, which is easier to integrate. Maybe you had sine, and you would definitely want to go sine direction, not arc sine, so you wouldn't use the inverse unless you really wanted to. What's another? Maybe is the equation in terms of x or y already. That might help. The next idea is one region versus two. Be wise. Save yourself time. For example, if you had the square root function, but then this line of negative slope came and capped off the region, making region R, surely you could do that both ways, x and y, but if you use x, how many integrals? 2, and y, 1. So that also would go through your head. If you have time, you could check with the other, that's fine. But that's another. And then also, this kind of goes to what it's a function of. This, for example, I would definitely use x because it's a single, or sorry, y because it's a single function of y, but this would be two functions of x, so it would be, all right. Calculator, no calculator. When it says calculator, if you're lucky enough, you get a calculator, free response area volume problem. That should be 9, automatic. But when you go to find the intersection points of the limits of integration, you must show 3 decimals, not just in your final answer, everywhere, in the limits of integration, in the intersection point, everywhere, and store them, store them, store them. Okay? Use the names if they give you f of x is this or g of x is that, use f and g in your setup. But if they give you y equals this and y equals that, you can't say y1. They don't take calculators. Okay? You can't say y1 minus y2 dx. That's a no. You don't do that. You use the actual equations, and you have to actually write them. Okay? Calculator's great. There's a pretty good bet you're going to have to do some kind of area without a calculator. Yeah, they're going to expect you to add some fractions. Sorry. Okay? I think you can handle it. Be careful. Be wise. Are you positive? That means you take steps to ensure positive, and that's done by using right minus left, which will always be positive, or upper minus lower, which will always be positive. If you get a negative, go back and change your work, not just your answer. All right, moving on. Volumes. There are three types, actually there's two little families of volumes, revolutions and cross-section, all right? I'm going to say that down there. So the revolution volumes, would you draw yourself a little coordinate axis and draw maybe a small slice this way. Now, if I had a slice like that against the x-axis, and then I revolved against the x-axis, what is made? That's a disk, okay? The volume is pi r squared times an h, and the height is some kind of d whatever. Now, in this case, it would be a dx or dy. Dx, okay, but if it were oriented so it's horizontal, then it would be dy, all right? Next, would you draw yourself a coordinate axis and draw that same kind of slice but floating above the x-axis? If you revolved it around the x-axis, then it would have a mirror image, and upon revolution it would make a washer. Okay? The volume for a washer is pi outside, big R squared minus little r squared, d whatever. Notice it's not r minus r all squared, which is different. And sometimes you do that for some types of problems, but this is r squared minus r squared. All right? I beg you again, use upper minus lower. These are around the x-axis, but we'll talk about axis of revolution, displaced axis. Three is if you have, a slice, say you have that same kind of slice here, but this time you revolved it around the y-axis. If you revolve that around the y-axis, then it makes a totally different type of figure, a shell, also called cylindrical shells. Volume is, remember the idea of an unwrapped long rectangle. If you take that and unwrap it, then the bottom edge is the circumference, and this is the height, so it amounts to something like 2 pi out front. And then the radius, which usually has to do with, it kind of depends, and the height. Those are both kind of funky. The height, though, isn't necessarily dx or something like that. The thickness is d whatever here, so there would be a d. Did I make a mistake? Okay. That's 3 dimensions, radius, height, and the thickness. Okay, we're done? Now, I'll say this, but it's not even worth saying. Technically, shells isn't on the AP syllabus. They always put a problem on where, so any problem can technically be done by washers or discs, but that doesn't mean it's the easiest way. So they will absolutely take shells, they encourage shells. It's just not on the syllabus, so you should be good. Either way, shells is crucial, so you should just, not to mention it's awesome. Yes? No, they're not. That's a great question. I totally forgot about that. Force and work problems are not. Force, they're not. Okay? All right. Using the axis of revolution. Oh, would you, I beg you, please type the pi in, or pi or 2 pi before the integral. The most common calculator mistake is failure to put in a pi. If there's a multiple choice distractor in there that's commonly chosen, it's on without the part. It's so focused on the integral, it's the part. Okay? Using the axis of revolution. Oh, this they're pretty harsh on in their grading. If you get something like a region like this, and it says, let's call that F and G, and it says around x equals -2, and you think, okay, so x equals -2, x is horizontal, x is a horizontal line, so it's this way, -2. Wow, you just took a 0 out of 9 on that problem. Well, actually, probably 0 out of 3 for this subsection, unless you, sorry, I freaked you out. 0 out of 3, sorry, you probably take a 0 out of 3. They wouldn't even look at, you have no chance, okay? Now, I totally understand why people think x equals -2 is horizontal, because you think horizontal, x-axis. But is this always x equal -2? No, this is x equal many things. Y is always -2. So I beg you, slowly, when you get a problem like this, slow and very carefully say, okay, x equals a constant is a vertical line. And y equals a constant is a horizontal line. Then if you just use right minus left and upper minus lower, then you're good to go. For example, if you said, let's say it was changed to around y equal -2. If you revolve that region around y equal -2, what approach would you use? Probably washers, because I didn't give you the functions. It's hard to say. I guess shells would be a possibility. But if you use washers like that, what's big R? F? Okay, so slow to judgment, go upper minus lower. What's upper? F. F minus -2. Big R is F minus -2, or F plus 2. What's little r? Upper minus, here's little r. What's upper minus lower? G plus 2, or G minus -2. You with me? Go slow. Okay? Cross-sectional volume. They are going more and more conceptual, I guess conceptual, that works. The idea then, just to take you way back to pre-algebra, not to insult your intelligence, okay? But the core idea, if you're good with the core idea, then you'll be in good shape. When I teach the volume formula in pre-algebra, I say, all right, we've got this plot of land, and we're going to build a building. Now, surely the area off of which you could build then affects how much volume you'll get when you make your building, right? That, in essence, says how much per level. And so you first calculate the area of the base to say, well, this is how much per level. And then you multiply it by the height, because you need to say, all right, I have 1, 2 levels, and boom, that's where area of the base times the height comes from. Now, volume then, area of the base times the height, is the big idea. The problem that you get in calculus is that the area of the base doesn't always stay the same. Sometimes this guy might start with this much land, but get bigger and smaller and so on, in which case you might have to either have an equation that governs it, or you might just say, you know what, I could do area of the base on the first level times 1 level, and that would approximate a little of the volume. And then I could recalculate another area of the base for another, and that would, and so it's kind of like estimating rectangles, but instead it's more like estimating cross-sectional volumes that kind of mock the thing. You with me? Now, if you were to do something that changed, that picture's messed up, that's ridiculous, then it needs to be more like the sum of many area of the bases times the height. That is the big idea that governs all. And after that, then you could go some kind of different directions. Maybe it says squares cross-section, in which case the volume is integral times, and the area of the base would just be a side square. And surely then you'd have to figure out, all right, is it x or y, and so on. Now it's important to know that these are not X or Y choices. They're prescribed. The minute they say cross sections are parallel to the x-axis is the minute they've decided this must be y and dy, not x. And so there's no choice to be had. It's set choice. Okay? If it says rectangles, then it's base times height, and each problem is different. Sometimes they say the height is 5, period. Or the base, or the height is 3 times the base, in which case I'd substitute 3 times the base and get 3 base squared. Those are different. You can have semicircular cross sections. Now that, the area of the base is pi r squared over 2, but we typically have the diameter to work with, not the radius. So if you then take that radius and replace it with half the diameter, then you get the idea that semicircles involve a pi over 8 of the diameter squared.
That's something you could start with on an AP test.
Absolutely. You do not need to show the development. I just was reminding you where it came from. You can just start there. And then equilateral triangle is once in a while. And the area of the base typically we use is 1/2 AB sine C. And given that it's equilateral, the sides have to be the same and the angle is 60 degrees. It eventually pans out to be root 3 over 4 of a side squared. And then isosceles and stuff like that. That's not even from there. It's pretty rare. Okay? Think your way through it if you get it. All right. Just remember, volume should always be positive. Volumes come out positive through skill, not luck. Upper minus lower, right minus left. Please draw. And they don't grade for your drawing, but it definitely helps get your act together. Please make double sure you're carefully setting up the region. You don't want to go and do all this calculus on the wrong region. So take your time. And on the AP exam, if it's a general kind of, hey, revolve y equals x squared and y equal 4 around the, whatever, around x equal 7, something like that, they don't, in a case like this, they don't look for the units. At least not correctly, I should say it differently. Okay. If you leave off the units, no penalty. If you put on units correctly, they don't care. If you put on the units and do them wrong, they do care. They count off. Okay? So you can gain nothing by putting on the units, but you will lose points if you do them wrong. Okay? So on these kind of problems, I would suggest don't put the units unless it's some kind of application problem where they're giving you the units and asking for them, then I would ignore them. Okay. All right. Switch gears to differential equations. These would be in...
What about arcs?
Oh, really spaced that up. Sorry.
No worries.
I didn't post it in. I'm sorry. Arc length, this is actually twofold. We'll give both, but parametric will do more on Friday. Arc length for a function, for normal y-x equations, arc length is 1 plus the derivative squared dx from x1 to x2, or if it's a function of y, it would be from y1 to y2 of 1 plus g prime of y squared dy. Notice that's f prime, not f. Guarantee you an answer of 1 plus f squared will be there. It's 1 plus f prime squared, right? Arc length and parametric, might as well say it today. Parametric arc length, which is equal to distance for parametrics, is from time 1 to time 2 of dx dt squared plus dy dt squared dt. You could also call those x prime and y prime. All right.
Wait, is there one area in this?
No, that's polar area. I think, right? Okay. Now you're making me doubt this. There's no.
No. I think I agree with that.
Yeah. No. 1/2 is in the polar area. Okay. Okay. Are we good? Is there anything else in this? Okay. Thank you for reminding me. Okay. Okay. Differential equations. A differential equation is one involving a derivative in differential form and possibly x and or y. Okay? So for example, y dx equals 3, that's a differential equation. dy dx equals x plus y, that's a differential equation. It's a non-separable differential equation. Okay, those are examples. I have seen one time in any free response where they use the other form, y prime plus xy, something like this. That is a differential equation. It's used a lot in some college level calc books, including the one they use at Mines. They use that a lot in the Rogaski book. You'll use that form mostly in 52. It's not a big deal. It's dy dx, okay? All right. Differential equations could be functions of the independent variable, the dependent variable, or both. I just said that, I guess. A solution to a differential equation is when you get rid of the derivative part to get the original y(x) equation. Now there's this huge gob that what makes this so hard, to me anyway, there's this huge gob of gray area here where with back substitution things could get totally wacky complicated here. Say you had this. Do you agree that dy dx in its most simple form is 2? And yet, by substituting the equation into itself, wouldn't you also agree that 2 is equivalent to y minus 2x? Yes?
I agree.
I mean, if I solve this for 2, 2 is equivalent to y minus 2x. So it's possible that they could give you this differential equation. Hey, the equation for this is y minus 2, dy dx equals y minus 2x. And you think, ooh, that must be something complicated. Well, in fact, it's actually, in this case, just a line. And they made it a little more complicated. That is the gray area. Those problems where it says, is there some kind of trivial solution, y equals mx plus b that satisfies, that's what's going on there. Now, those are pretty rare. And I don't want you to focus on those. You've seen a couple more than, I guarantee you, more than most people, guarantee. But that's not something you should sweat. If it's there, roll with it, but it's not something you need to sweat. Okay? Slope fields give you visual clues to a solution to a differential equation. For example, this problem cannot be separated and integrated back to xy. It's a non-separable differential equation. And yet, by slope fields, you could actually get a picture of what the graph, the y-x graph, could look like going by what the slopes are. In terms of saving you time, now, you guys are pretty fast, but in terms of some time savers, I might look at this and say, well, I know slopes are 0 if x equals y. So I could write a ton of slopes by just saying here, 0 slope, 0 slope, 0 slope, 0 slope, 0 slope, 0 slope, 0 slope. Boom, just got 7. Okay? Look at those kind of time savers. Then you might start to see other trends in there, positives and negatives and that kind of thing. This is way more points than they would ever have you do on an AP test. The most they would have you do is maybe 2 in each quadrant, maybe 10 or 12 or so at most. Okay? Is this all? Do you want to practice this or no? You got it.
Got it.
Okay? I'll tell you what. If we wanted to graph the particular solution through 1, -1, let's just do enough slopes to do that. Okay? So if I'm starting at 1, -1, this is actually nicely into Euler anyway. So 1, -1 is there, yeah? What is the slope at 1, -1? 2, yeah, so it's pretty steep there, When you go to do this, imagine a point up 2 and over 1 away and point in that direction. Okay, so if I follow that to the next point, that takes me to 2, 1. Do you agree? Okay, on the right side. 2, 1, what is that slope? 1. Okay, so that's a little flatter now. And if I follow that slope, that takes me to 3, 2, yes? And what's the slope there? 1. Okay, so it feels like it's starting to flatten out there. All right, and then I could go back. Instead of going up 2 over 1, I could also go down 2 over 1, which would take me to 0, negative 3, I believe. What's the slope at 0, negative 3? 0 minus negative 3 is 3, so it's a little steeper there. So it feels like the particular solution would flow like that, right? It's really what you're doing when you do Euler. You're doing little chunks to the next point and changing the derivative as you go. Many solutions are curved. Most solutions are curved. You see this curving kind of behavior here. But if you were to carry this out, we said this slope is 1 and that slope is 1. That's pretty common. Say you went this slope is 1 back to here. What's the slope at 1, 0? 1. Okay, 1 minus 0 is 1. What's the slope? That takes me to 0, negative 1. What's the slope there? 0 minus negative 1 is 1. That takes me to 1, negative 2. That's 1. So you can see that although most of these are curves, there is this linear solution in there. That's sometimes that crazy linear case they ask. If they ask, what is it? What would you say? The slope field actually tells you. What's the slope field? The slope is 1 and the y-intercept is negative 1. Let's start with that theory. If the line is y equals x minus 1, how? Well, let's do y dx. It is 1, but what is 1 equal to? Isn't 1 equal to x minus 1? And so that's how they're getting that craziness. All right, are you with me? Okay. Matching a slope field to a differential equation. I beg you to use zero slopes and undefined slopes. That's the easiest way to eliminate multiple choices. Okay. Then, if it's a product or a quotient, use signs in the quadrants. What's the third method I was looking back? I can't remember what third one. The fallback, maybe the one that you might use to choose between, narrow down all the way to 2 different choices, then I might go point by point. But maybe zeros. I kind of see the slopes there. I can't remember what I was thinking about in the third, but whatever. At any rate, point by point is amateur hour. That's a time meter. You want to use that as a last gasp kind of thing, okay? All right. So, for example, if I said, which one of these equations makes this slope field, give that a thought for just 1 second. I just used the first quadrant sign and I already eliminated 3 choices. So what do you say, B, or do you agree that A, C, and D all yield positive slopes in the first quadrant, so they're gone? Do you agree? Okay, so what do you say, B or D? B. Oh, now I remember what I was. This is, do they vary horizontally and or vertically? that would tell you whether to expect x and y at the end of the equation, or just one of the other. That was what I was looking at. I'm sorry, what did you say? Let's say I go, if I go here, then this would be, I would probably need to go in a negative x place, wouldn't I? So in this quadrant, in a negative x, this guy would be negative, sorry, I'm so slow, negative over positive. That is a negative slope, and that's a positive slope, so that seems like a, no, am I right? That's right? Did I make a mistake? Is that right? Oh, that's a positive, and that's a positive slope. Is that what you're saying?
Yeah.
It is a positive slope, I agree. Okay, so that's a yes, and that's a no. You could also, I guess, integrate it. If you know if you could easily integrate it, that's a possibility. How about this? Where are the zero slopes? Where is the slopes of this? Where are the slopes here of 0? At y equals x or negative x? Oh, sorry, here, yes, but the equation? This would be 0 at y equals negative x. Is this 0 where y equals negative x? No, it's 0 where y equals positive x. This would be 0 where y equals x. Do you agree? That fits like that could be it. This would be 0 at y equal x. That seems like it is a possibility. Is this 0 where y is x squared? No, that's definitely not it. And this is definitely not it. Y is x squared. Is it? So that right there, just 0 slopes, gets me down to B and C. And then you could choose based on stuff. Maybe just the slope at 1, 0 even. The slope at 1, 0 for this equation would be 1, but that slope looks like it's negative 1, so that doesn't feel right. At 1, 0 here, this is negative 1 plus 0, that feels right. So I'm feeling C. Are you with me? And then I don't know what that question is, so ignore that. Okay, matching a slope field to a regular equation. This is one of those great gotcha questions. Imagine if I had a slope field that looked like this. Boop, 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 boop. And it said, which of these is the equation for? And it said, dy dx equals cosine of x. Yes or no? No. Okay, because you're trying to fit the solution curve. This would be y equals cosine of x. Dy dx would actually be negative sine of x. And so be careful in distinguishing solution curves versus the differential equation. You should be able to graph these on top of the slope field. Graph the solution curve on top of the slope field and say which one matches. Okay? So, for this case, for example, which of those equations matches those slope fields? If you did a graph here, what does that feel like? X cubed. It is B. Yeah? How about this? Which of these kind of has that look to it? Ooh, close one. This feels like a maybe, but gosh, it sure does look horizontal there. I don't know. This is ridiculous. That's just ridiculous. What does this look like? It has a vertical asymptote, which we don't know if they're showing that part, but we also, oh, it would have a vertical asymptote at 2, wouldn't it? But we also know that this should be, by end behavior, x-ish, yeah? So that feels wrong. Does this have a horizontal asymptote? Yeah, this has a horizontal asymptote at 1, which this feels like it doesn't have a horizontal asymptote at 1. I thought that was it, quite frankly. So are we feeling natural log? I guess so. I was thinking the asymptote. Okay, solve your differential equation. Would you circle this like that and put stars by it? And put do this. Because the saddest words on all the AP grading is 0 out of 6 if you don't separate the variables. 0 out of 6 that don't even look at it. What do you want? I don't have it. let me get you a blank one. Oh, you can use that. All right, so make sure when you get a differential equation, you separate the variables. Understood?
Yeah, I did a lot today. Thank you.
Okay. Integrate both sides, plus C on both sides. Please pay attention to what the variable of integration is. But based on this is the gotcha to this. If you see a separable differential equation, I beg you, do not do a fundamental theorem approach unless there's a last resort here. If you do this as some kind of W is this, you're going to get pretty much nothing, okay, or nothing. Okay, so don't, if it's a differential equation, separate the variables. Pay attention to what you're integrating with respect to. See how much I have left? Oh gosh, you probably need more review on logistic than that. Okay, so let's, if I have time, I'll come back to that. Let's go to logistic though, shall we? Okay, in BC there are two famous differential equations you must have absolute familiarity with. They do not have, thankfully, they don't have Newton's law of cooling on there, which they should, quite frankly, but maybe we'll talk about that later. All right, exponential growth or decay. The differential equation is y prime equals ky, or dA dt equals ka. Either one of those, population, you could use p, whatever. The integrated equation is y equals y initial e to the kt, or a equals a initial e to the kt. And, oops, the verbal description is the amount rose at a rate proportional to the amount. Think compound interest. How fast your money grows depends on how much you have in the bank at that moment. The more you have, the faster it'll grow. Plus the interest rate, which is the K. Okay? The sketch is if K is positive, then it is exponential growth. And if K is negative, it's exponential decay. Logistic growth / decay. That's when the amount grows or decays at a rate proportional to the infected and the uninfected. Or you could say proportional to the how many there are and how much room for growth there is. Okay? A differential equation is y prime equals ky L minus y, or if you like, dp dt equals kp L minus p, proportional to the amount and the room for growth, which is the difference. I remind you, L represents the carrying capacity, and so once it starts to approach that upper limit, that's then where you're topping off. It's population as a function of time. The integrated equation, you don't have to show all the work, which involves separation of partial fraction decomposition and all this crazy integration. It is just the population equals L over 1 plus, did I call it A or E? B for you. B. E to the negative LKT, where B is the room for growth over the range. Okay? That was the carrying capacity, which you'll be able to find in the differential equation. The K will be in the differential equation. So here, looking at this, this is exponential growth or logistic? It's logistic, okay? What's the K? Actually, we're not ready to determine the K. We want, in this case, to play around with this a little bit And so I would take the time, there are two forms, and I want you to be aware of this. If I get a common denominator in here, and then bring out the denominator 30, it's 2/30 y 30 minus y. At that, then, it looks like our form. Okay? I don't want you to memorize two forms. So, what's the k? 1/15th. And what's the L? 30. Okay? Sometimes they ask limits here. If I said, what does the population or y approach as time goes to infinity? What does it approach? 30, the carrying capacity, right? Okay. If I tell you this, then that allows you to find the B. L minus P initial over P initial. What's L? 30. What's P initial? 3. And what's P initial? 3. And so that is 27 over 3, or 9. Now I'm ready to write my equation. The population is L on top. What is it? 30 over 1 plus B. What's B? 9. E to the negative L. Negative 30. What's K? 15th, and T is obviously the variable. Okay? All right. When is the max growth rate? Fastest growth? When the population is half the carrying capacity. Okay? Put in here, as time goes to infinity, the population approaches the carrying capacity, and the rate of change approaches 0. Okay? Okay. Euler's method is used to estimate,
I don't think we're gonna get through.
shoot, the y value given a differential equation. All right, we'll finish that tomorrow. Maybe we can write it. Do you remember it enough to do those problems tonight? X
So that's,
y2 equals y1
you should all be okay, right?
plus
So you also still okay, right? So we want something else.
out of the day.
What?
So because we took an emotional picture of